Blind source separation, short BSS, is a well-established model-based framework which recovers latent meaningful components from the observed data alone. Temporal blind source separation, short TBSS, refers to a subset of BSS methods that specifically account for temporal correlation. TBSS, like for instance principal component analysis, is a method independent to a particular application domain and separates observed data into a linear combination of univariate components. We present TBSSvis, a VA prototype to support analytic tasks involved with TBSS. In this video, we demonstrate these analytic tasks using a dataset of 23 currency exchange rates to euro. The point of such an analysis could be to, for instance, find the most volatile components and bet on the involved currencies on the financial market. Prior to the first view, the analyst prepared the dataset as a CSV file and loaded it into TBSSvis. This view shows the input data in a space-efficient way. The 2008-2009 global financial crisis is readily visible in many input variables. The analyst proceeds to the next screen. The analyst first inspects the component similarity projection to compare the similarity between recovered component sets. They select one outlier and one other for more detailed comparison. Related data are now highlighted in all views. The analyst looks at the table to see if their parameters were any different. It is visible that each member uses one leg set exclusively. The analyst takes a look at the component overview to investigate the similarity of the red and blue member to each other, but also to the rest of the ensemble. As the blue marks appear scattered and/or of low opacity, it confirms what was visible in the component similarity projection. The analyst compares the components of the two members in detail. The slope graph shows that components 2 and 3 are identical, and a few others very similar. With TBSSvis, the analyst is also able to inspect results on a technical level that they might be interested in but usually do not have the time to compute. The top line chart shows a measure of temporal structure, which is also used for the leg selection guidance. It is visible from low values and non-existing patterns that the input data is very noisy. The analyst now wants to try a new parameter setting and see how it compares to the red and blue member. First, they pick a weight in the 0.9 range, as the analyst expects components to correlate mostly linearly, and proceed to the leg selection. The analyst expects exchange rate data to exhibit high weekly correlation and adjusts the legs to weekly resolution. Looking for the most promising legs, they filter for those where variables exhibit high autocorrelation. As expected, only quite short legs up until a year or so remain. The analyst interactively selects K1 legs based on the guidance of TBSSvis, accepts the defaults for K2 legs, and is then redirected back to the Explore screen. The new ensemble member is automatically selected once computed and is assigned the next possible color, in this case green. The analyst again opens the component comparison view to inspect the components of selected members in detail. They adjust the plotting order to compare the green member to both the red and blue simultaneously. They see that their custom parameter setting produced a result mostly similar to the red member, but some new components were obtained as well. The analyst wants to see how these components were formed and looks at the loadings in the unmixing matrix. For example, component 12, which was only in the new green member, is mostly influenced by Australian dollar. Hong Kong and US dollar appear to influence many components. It is also visible from more bright tones in the matrix visualization that the separation quality increased. With one click, it is possible to export candidate results to a file format supported by the analyst's current tool, where the data processing pipeline continues. Please see our paper for more details.